how we can relate the various uh, the various topics in medical research, and how it is to conduct research knowing the subject of biostatistics, because without biostatistics research methodology is incomplete. So that's why it's very important to learn the subject of statistics. At least the basic concept should be understood by all medical professionals, so that when you conduct research, you should know the nuances of, um, the finer points of conducting the research. So, without any delay, I am starting my screen. You just let me know when you
Yeah,
are able to see my screen.
yeah, yes. You can share it, ma'am.
Uh, just a minute. So can you see my screen?
Uh, yes, ma'am.
Okay.
Uh, Please maximize it, ma'am, on the full
Yeah.
screen. Yeah,
Yeah.
okay.
So
Now it's okay.
this is what the topic is. The topic is on importance and role of biostatistics in medical research. So, so what statistics actually starts with the definition of statistics. Carl Pearson has defined statistics as the grammar of science. And even Ernest Rutherford, who was a physicist, he has said that if your experiment needs statistics, you ought to have, let me minimize all these windows. You ought to have done a better experiment. And then even Davidian and Louis in 2012, which is not very old, they said that statistics is a science of learning from data, and measuring and controlling and communicating the uncertainties in the data, and thereby providing an essential way of controlling the course of scientific and societal advances. So, statistics has been defined by different persons. It is actually a study of collection, analysis, and interpretation, and presentation and organization of the data in simple and plain terms. So, I'm not able. Okay. So there are three branches of statistics. One branch is the applied statistics, where it contains in the usage of statistical applications in different areas and domains. It uses the descriptive statistics, and the applications are widely used in inferential statistics. Then comes the theoretical statistics, which deals with the theory behind applied statistics, and it consists of various rigorous methods that provides ways of proving the statistical techniques. While mathematical statistics is also one way of dealing with the techniques applied in the applied statistics, and it deals with the mathematics part of it, the theory behind it, and it is no way different from the theoretical statistics domain, where it uses probability theory, linear algebra, measure theory, and various other computational techniques to derive statistical conclusions. So the broad three areas where statistics is applied is applied statistics, which we generally do as applied statisticians, and many of the doctors also, they once they learn statistics, they try to become applied statisticians. They don't understand the theory behind it, but they know how to apply it using statistical tools, the computational tools also. But whenever we apply statistics, we should have a fair idea about the theory behind what's being applied, so that the rigor is not lost. So, biostatistics is a collection of procedures and principles for gaining and processing information related to biomedical sciences. And it helps us in making decisions when there is uncertainty. It is a tool by which we can make informed decisions to improve human health, and it encompasses a lot of statistical techniques that can be applied for uh, um, arriving at conclusions regarding human health. We all know that human health is largely determined by genetic and environmental factors. Diseases do not have a simple etiology. We are all living in a COVID era, and we are still trying to understand the etiology of this disease, and the epidemiology and the pattern of the disease. The disease doesn't have a simple etiology, and it has multiple factors and multiple promoters. There is no silver bullet of treatment for any disease. There is a lot of variability in the genetic makeup and the environmental exposures that could possibly act as confounders and hide the real impact of any particular factor on the disease. There is a general tendency of having patterns of disease among the human population that may then result in different research data, which we try to analyze using the statistical techniques. Our main job as a statistician or a biostatistician is to investigate these patterns in different patients, their families, and as researchers, draw inferences of the population based on a small set of data. That is what is biostatistician's main job is, and that is how he plays a major role in research methodology also. So, so we therefore we can say that a sound medical research requires a careful synthesis of expertise of many disciplines, including genetics, epidemiology, and statistics. It's very difficult to deliver lectures online, what's happening. So, talking about the role of biostatistics in, can we minimize this? Because it's coming on in my slide. I'm not able to show my slide properly. The role of biostatistics in clinical research. When we talk about the role of biostatistics was first introduced in clinical research in 17th century, and the primary steps or primary areas where it was very much used was in the development of protocols and management of the data, in implementation of the studies, in study monitoring, in data analysis, and in report writing. As we all know, biostatistics is very helpful in evidence-based research and in drug development. As we see in this slide, the drug development process takes years, about 10 to 15 years, starting from the initial stage when about 5 to 10,000 compounds are analyzed, and they reduce those compounds to a smaller number, say 250 or so, in the preclinical stage, and thereafter when the compounds are ready for clinical trials, they are only 4 or 5 in number. After that, there are several phases of clinical trials: phase 1, phase 2, phase 3, and then phase 4, after which the drugs are ready to be marketed. And then in the phase 4, the post-marketing surveillance is done of these drugs. So there are several steps involved in the development of drugs. And in these studies, the importance of biostatistics is profound. Now, once the drugs leave the preclinical stage and enter the clinical trial stage, the researchers have to register the clinical trials in a clinical trial registry. Now, the clinical trial registry of India is run by the ICMR, and it is housed in the National Institute of Medical Statistics, where the researchers, before they actually start the clinical trial, they have to register the clinical trial in the registry, and they have to give details of the clinical trial, including the numbers, the sample size, the design, study design, and the drugs that they are going to test. And once the clinical trial registry registers the trials, it, the as we keep on as the researchers keep on adding patients in the trials, trial the clinical trial registry database keeps expanding. So that's what we do in the ICMR clinical trial registry. Now, this is the Indian registry, and this is the only registry which is supported by the WHO on clinical trials. And apart from that, there is a global registry also, which is called the Clinical Trials GOV under the NIH that registers global clinical trials. So, once the drug development stage crosses the clinical trials, my God, there's some problem in the mouse. Just a minute. So, the conduct of clinical trials goes through several steps, starting from the planning stage, and then the protocol is applied on that, and the patients are recruited. The first patient is recruited, and then it goes on till the last patient is recruited, and thereafter the data that is that gets collected in the clinical trial database is analyzed by the statistician, and after analysis the reporting of the trials is done, and thereafter the drugs come into the market. Now, a biostatistician is required at the initial stage of the clinical trial, at the pharmacokinetic and pharmacodynamic studies. When it is conducted, a biostatistician is required to check whether one needs to do a superiority study or a non-inferiority study or an active control or an equivalence, bioequivalence study, whether one has to conduct a dose response study or it needs to be done as a safety follow-up study. So in all these stages, the biostatistician's role is very important.
Ma'am, please unmute yourself because we are not okay.
Yeah,
Yeah.
it's better. Now you can hear me, no?
Yes. Yes. Yes.
So there are different study designs in a clinical trial. The conventional design is a parallel group design. Then we have the crossover designs where the drugs are given for a time period. Two drugs are given for a time period, and then there is a washout period after which drug A is given to one group and drug B is given to the other group. So there is a crossover design and the parallel group design. There are other types of study designs also, like the titration design. We don't go into the details. I'm just trying to build up a scenario of how biostatistics is used in these studies. Then we have the cluster randomized designs and other types of designs. Now, the biostatistician's role in all these studies is um primary right from the beginning when the study designs are chosen. It we need to use the expertise of a biostatistician for selection of the control, whether you need to have a placebo control or a positive control. During the randomization process, one has to decide whether randomization is necessary or not for a clinical trial. If at all randomization has to be done, do we need a cluster randomization or an individual randomization? Is it feasible to do randomization in a particular site? And then what are the various randomization algorithms? There are various randomization algorithms in a clinical trial. Then the blinding process, again, a statistician's uh, importance comes because blinding may be done at a patient level or at the clinician level, and sometimes statistician plays as an evaluator, and if he plays as an evaluator, then probably then he should also be blinded. And sometimes statisticians play a role as a third party expert, where he is not actually involved in the clinical trial, but he is the one who gives who has all the envelopes and the randomization procedures with him. So the statistician is the person who deals with all these steps right from the beginning of the clinical trial. And of course, sample size calculation, we all run to a statistician whenever we need to calculate a sample size. And that is one of the most important role that a statistician plays in a clinical trial. Then comes the data analysis stage where depending on the type of data, the analysis is conducted. If it is a continuous data, then those tools that have to be used to analyze continuous data are used. For categorical data, the tools are different. The analysis and the inference patterns are different. And if one has to conduct a survival analysis, which is a time to event uh, approach, there again, the analysis is very different and the statistician's role is very important. So biostatistics is actually the foundation of uh, generating clinical evidence, and it plays a very important role in all phases of drug development and in other clinical trials and other study designs. So again, coming to the point that biostatistics plays a very important role in clinical trial and helps in clinical decision making. It helps in minimizing bias. The statistical tools help in minimizing the bias, identifying confounders, helps in hypothesis testing and other various steps uh, in conducting a research study. So this gives this slide gives the gist of the role that statistics as a subject plays in clinical research. So as I said, in order to conduct a clinical research, we should have the basic statistical literacy of not merely computing the statistical formulas. You don't, as a medical professional, you need not compute the statistical formulas or even do a statistical test, but at least you should have the um, uh, power of reasoning and understanding and interpreting the data that a statistician provides you. You can go with your data to a statistician and you'll do all the analysis that you want, but unless you understand what he has done, you will not be able to take a decision on your data and draw inferences from your data. So it is very essential to critically build the skills of critical thinking, and you should enhance the ability to explore, understand, reason, and evaluate the data that comes to you in the form of a research data, and that will ultimately lead to evidence. And then you should be able to develop the fundamental skills to review. So statistical techniques not only help you in clear decision making, but it also helps you in reviewing and appreciating research articles that you keep reading in medical research, and it helps you in critically appraising these studies carefully and understand the findings of these studies, so that the same techniques can be applied by you also in your research studies. So it helps you in developing a conceptual framework. Now, talking about the topics of statistics that one should learn as introductory statistical topics is we don't go into the details because there are other resource persons also taking these topics independently. But today, what I am just going to tell you is that the introductory statistical topic starts with the description of the data. So the data has to be described in various ways. What are those various ways? We'll see. It has to be, once the data has been described, you have to draw summaries from this data, because data may be a collection of lot of numbers, but unless you make sense of that data and in a manner that is easily communicable, and you can communicate your findings to the audience at large, it doesn't make sense. So you should be able to describe your data in a manner easily understandable to others, and then also quantify the data into summary forms, so that when you communicate or when you do further data analysis, these summaries are useful. And then the concepts of probability is very important in introductory statistics, because everywhere we talk about p values, the probability of inclusion in a what do you call, in a group, in a clinical trials, all that comes from the concepts of probability and probability distributions. Then then we have to talk about, once we have described the data, summarize the data in a manner which is understandable to the audience, and then you have used the concepts of probability. Then comes the uh, study of association and study of relationship between different different numbers or different concepts. So the study of relationship is through correlation and various other. It's not only chi-square test of independence, but there are many other ways of studying the relationship between data sets and data values, which are called variables in statistics. And then we also need to know how statistics can be applied in estimation and hypothesis testing. So decision making is done using estimation and hypothesis testing. So I'll be touching these things in a little, only a little bit, but the other things, other speakers may be giving details of that. But then I will quickly go over to various study designs. So then, quickly going to the introductory topics, we said that the data that we have collected has to be described in a manner to communicate your findings. So there are two ways of describing the data. One is through numerical descriptors, and the other one is through graphical descriptors. We all know what is mean and standard deviation, and mean and standard deviation are the commonest kind of descriptors for continuous data like height, weights, blood pressure, blood sugar, and whatever. And then there are the other kind of descriptors which are used for categorical data sets like gender, race, then maybe the color of the skin or the color of the hair, and many other, maybe the staging of cancer. So in all these places, categorical data is used, and the numerical descriptors for categorical data are generally percentages and frequencies. Then there are different types of graphical descriptors. These are contemporary graphs like bar graphs, line graphs, histograms. Nowadays, the data scientists come out with many other types of graphs also, which are easy pictorial presentations of your data that describes your data in a manner easily understandable to others. So these are some of the descriptors of the data. Then after the descriptive statistics is conducted or is presented by the researcher, then comes the inferential statistics that looks at the patterns in the data and draws inferences for the population, because you all know that you cannot collect data for the entire population that you are interested in. So you will always be taking a sample of that population and then draw inferences based on the sample. So these inferential statistics helps you in drawing inferences based on the statistical theoretical theory behind that. And then we estimate the numerical characteristics of the data, and that is called the estimations, and then describing the associations through correlation. Then the different types of data, along with studying the association of different types of data, one would be also interested to know whether many data points are connected with each other or not. Does one data point have an impact on the outcome? So if that is the kind of relationship that you are interested to look at, then we do uh, mathematical modeling and regression modeling. And then based on the regression, prediction is done, extrapolations are done, and various other techniques are also used in inferential statistics. So this is an example of tabular kind of data description. If you see the first table here, this table has all numbers because you're looking at the blood glucose, and the glucose is categorized into less than 7 mm and more than 7 millimolecules per liter. And if that is the kind of categorization that is done, and you're looking at various age groups, then this kind of tabulation is the frequency table. It's a frequency tabulation, and you have the percentages here. And this is one way of tabulating the categorical data. But if you are looking at a continuous data, then you cannot put them into categories. Then you have to look at something called the summary measure. And the summary measure could be the mean, the median, the minimum, the maximum, or maybe standard deviation, standard error, all this. So these are various ways of describing the data in a tabular form. But if you are looking at the description of data in a graphical form, we see here the bar graph, where the bar graph is used for pictorially presenting the group data or the categorical data. And if you see the second picture, and that is the histogram, which is used to show the distribution of continuous measurements. And then we have line graphs that show you the pattern of the data over a period of time. We want to see how the data changes over a period of time, then we use the line graphs. And the pie charts are used when one looks at proportion of contribution of any particular category in the entire group. Say, for example, if you're looking at the various, these are actually, I think it is, let me see. Some percentage it is. And if one is looking at yeah, this is the percentage. If you want to see the categorical data and the contribution of each category in the entire group, then pie charts are used. And then when we have to see an association between two continuous measurements, then the scatter plot is also used, where the scatter plot gives you the association between a continuous measurement on the x-axis and a continuous measurement on the y-axis. So these are the different, and there are many other graphical methods, and these are the common ones. Then there are some statistical graphs like the stem and leaf plot. This is the stem and leaf plot that gives you an idea about the distribution of the data. See this, if you see this, there is a distribution of the data. This number 70, 72, 74, 75, 77, they are more in number. So this gives you a frequency distribution. And in papers, we have the box plot also, which is a complete description of the data starting from the lowest value of the data. And it is used only for describing continuous data, where you have the lowest value and the highest value. It gives you the percentiles, how many, what percentage, what proportion of people or what proportion of measurements fall below 25% below that number and 75% above that number, the median, the mean, the upper or the outliers, all that is given in the box plot. So it is a complete pictorial presentation of the raw data. So, and then comes the numerical summaries. So if you look at the numerical summaries, we summarize the data based on the type of data that we get. There are two types of data: categorical data and continuous data. Now, the categorical data are again grouped into two categories, and they could be either nominal data. The nominal data, which are nothing but categories which are mutually exclusive, and they are not ordered. Like for example, male, female. You cannot order them as male and female, or maybe the names of the different towns or cities. They you can just name them, but you cannot order them or give them any numbers which has a meaning. Now, the ordinal data are those groups of data which are again named categories, but they can be ordered. Say, for example, the disease stage. Now, the disease stage, if the disease is mild, you can give that a lower number, and if it is a moderate stage, then you can give a slightly higher number to it, and then the severe and various other stages. So we know that the higher number is is more severe than the lower number. So it has an ordered structure. If you look at the quantitative data again can be discrete or continuous. Discrete data are integer values. They are typically counts, and they are lesser in number. Uh, Say for example, the number of days a person is sick in an year, which is very with the number could be very small, or it could be continuous values which take values in a range. Say, for example, weight, height, blood pressure, blood sugar, any other such numbers. So, numerical summaries are again based on the type of data that is collected. So, now next comes the derived data. The derived data. These are data numerical summaries which are derived straight from the data, but the derived data are numbers which are created from already existing data. For example, percentages. That gives you the number of events per 100 events. And the ratio. The BMI is an example of a ratio where from weight and height you can calculate BMI. So these are all called derived data, rates, events occurring over a period of time, or the rate of change of an event, or the scores that is calculated based on certain parameters. So all these are called derived data. Then, so once we describe the data in a numerical form, then the next step would be to summarize the data. The summary of the data could be done either using the arithmetic mean, which we all know is the sum of observations divided by the number of observations, or it could be the median, which is the middle observation that divides the entire data set into two equal parts, or it could be the mode, which tells us the observation that occurs the maximum number of times, or there could be other measures of location. These are called measures of location, data summaries. And there could be other measures of location like the geometric mean for a skewed data set, or it could be an arithmetic, I mean the harmonic mean, or it could be a weighted mean. So these are all various data summaries that could be used as measures of location, and they are single numbers that provide you information of the entire data set. Something is wrong with my mouse. Work. Okay, I just have to click. Okay, so when do we use the mean, the median, and the mode? So what we do is that whenever we have a collection of data, we first see how the data is distributed. So how do we see the data? You must have learned in your 10th and 12th class how to draw frequency distributions based on the raw data. So the distribution of the data is seen using the frequency distribution. And if you see the different shapes of the frequency distribution on this slide, you'll see that sometimes the frequency distribution is symmetrical, and sometimes it is skewed either in the positive direction or in the negative direction. So based on the distribution of the data, the various summary measures are also used. If you have a symmetrical distribution, then the most common summary measure is the mean. And if the data is skewed on either side, then the median is the best summary measure. The various advantages and disadvantages of mean, median, and mode, the geometric mean and the weighted mean that is listed in this slide. The main advantage, the mean is the most advantageous summary measure otherwise, except that it is highly distorted by outliers, and it is distorted by some skewed data. If you have a the data on blood pressure of say 500 patients, and even if one patient's blood pressure has been recorded as 250, it could be either a mistake, or it could be that the instrument has not been properly calibrated. What will happen is that the mean blood pressure gets distorted. So it is distorted by outliers and by extreme values. While the median, which is the central or the middle value of a set of data, doesn't get distorted by outliers. It and it doesn't get distorted by skewed data. But the disadvantage of using a median is that it ignores most of the information. It doesn't get impacted by extreme values. As a result, it also ignores those extreme values, which could possibly be useful values for our analysis. And the mode is the worst kind of average or summary measure one can think of for a continuous data. It is not at all useful for at least medical and clinical research studies. And the geometric mean is useful, but it is only appropriate if the log transformation is possible. And the weighted mean is again a very useful summary measure. It has the same advantages of a mean, except that the weights must be known and it should be estimated. Now, as we have the measure of location for describing the data, we also should also know the measure of dispersion. Now, what is the measure of dispersion? Measure of dispersion tells you how varied, how different uh, the data are from the central value. And what is the central value here? The central value could be the mean or the median. So it gives you an idea about the dispersion of the entire data set from the central value. Now, the simplest and the most simple measure of dispersion is the range, which we all know, maximum minus minimum. Then the other useful measure of dispersion is the standard deviation or the variance, which is nothing but the sum of the square of the deviations of the values from the mean. And if you derive a standard deviation from the sample for a population, it is just the sum of squares of the deviations from the mean divided by the number of observations in the population. Population means a large group of persons. But if we are selecting a sample from that population and trying to arrive at the standard deviation value, then instead of the denominator being the number of observations in the population, it will be n minus 1. N is the number of observations in the sample, and it will be divided by n minus 1 instead of n. Now that is the second measure of dispersion, and the third one is the quartile deviation or the interquartile range, which is the uh, and a quartile is one which divides the entire data set into four equal parts. There are three quartiles in a group of data, and it divides the entire data set, an ordered data set, into four equal parts. And that's what a quartile is. And whenever we have a skewed data set, then we do not we as we saw in the earlier slide, we do not report the mean, we report either the median or the quartile, median and the interquartile range. So there are a lot of advantages again for these measures of dispersion or spread. The range is a useful and easily determined, but it has disadvantages that it takes only two observations into consideration. The variance is a very useful measure, but algebraically it is difficult for people who are less oriented towards mathematics to calculate the value of variance. And same is the case with the standard deviation also. Although these two, standard deviation and variance, are the most important measures of dispersion for most of our studies. Now, quickly going to the next topic, and that is the study of association or relationship between variables. Correlation is the concept that tells us that helps us in examining relationship between variables, and it helps us to understand whether there is any linear relationship between two or more data points or data variables. And these are the various patterns or relationships that can be seen between different types of variables. It could be a very uh, straight line and an increasing pattern. As x increases, y also simultaneously increases, giving you a straight line pattern that tells you that there is a single linear relationship between x and y. Or it could be the other way around: as x increases, y decreases, that again in a very perfect fashion, and that gives you a perfect correlation of correlation varies from -1 to +1. This is +1 correlation, and this is -1 correlation. Or there could be absolutely no relationship between x and y, and then it becomes a straight horizontal line. Or it could be a curvilinear kind of a relationship. So we will not go into the details of all this. Then comes the importance of statistics in decision making. And statistical decision making is done using hypothesis testing. How do we do hypothesis testing? What do we do in hypothesis testing? We have to always understand that statistics is a subject that came into existence because the primary reason for its existence, as I see, is that we are not able to enumerate the entire universe. So therefore, we need to take a sample from that universe. And when we take a sample from the universe, you are liable to make some errors. And when you make those errors, you want to quantify whether what percentage of errors you have made. And therefore, there is this subject called statistics that helps you in measuring the uncertainty and measuring the errors and measuring the of deviation of values when you deviation from truth, I mean deviation from truth, when you take a sample of values from the entire universe. So that is what this hypothesis testing also tells us, how to take decisions based on a small sample when you draw a small sample from a larger universe. And this is based on the sampling theory, which works on samples of data and on probability distributions. And we call the probability distribution of the sample as the sampling distribution. And this is again, I will not go into the details I just want to emphasize the fact that the larger, whenever we go to a statistician and look for sample size, he will, if you should always remember that the sample size should be large enough to represent the entire population, but it shouldn't exhaust your resources. The purpose of drawing a sample size is that it should be large enough to represent the universe from which the sample has been drawn, but it shouldn't be that large that it exhausts all your resources, because you have to put in resources to do the uh, research work. So what the central limit theorem is, the basic theoretical concept on which sampling distribution is based, which says that as sample size increases, the shape of any distribution, we learned about the frequency distribution, the shape of any distribution, skewed or whatever, becomes a normal distribution. And what do you mean by a normal distribution? A normal distribution is a bell shaped curve like this, the red one. It is a bell shaped curve, and this is a skewed distribution. It can be as skewed as possible, but if you keep on increasing the sample size, it becomes a normal distribution. And when it becomes a normal distribution, many of the problems that one encounters in statistical decision making reduces if you get a normally distributed data, because every hypothesis test has an assumption of normal distribution. If the data does not follow a normal distribution, many of the tests that you apply may not actually be valid. So that is why one insists that one should have adequate sample size to not only represent the universe but also to mimic the normal distribution. So I am just giving you a small idea about what sampling distribution is. Suppose there is a population of size 4. There are 4 persons in the group, and one is interested to look at the average age of these individuals. So this is just a small example. So we see here 4 persons, and their ages are 18, 20, 22, and 24 years. And we are trying to see what a sampling distribution means. So we calculate the summary measure of the population. This is a population of 4 persons. So we calculate the mean and the variance using the formula. Mean is the sum of all observations, sum of all ages divided by 4, and the standard deviation, as we all know, is the variance is sum of squares of the deviations from the mean, and the standard deviation is the square root of the variance, and we calculate this mean and the standard deviation for this data set. Now this is for the entire population. Suppose suppose you are not able to study the entire population, which is the normal case when we use statistics. You are not able to study the entire population, but you take samples from that population. Say, for example, in this study also, we have a population of 4 persons, and if we are drawing samples of 2 each from this population, so how many such samples can be drawn? Sorry, just a minute. Not able to see. Can you see this? Should I make it bigger? Because it doesn't come.
Yes, ma'am.
I'm not able to show it in the slideshow somehow. But let me show it this way.
Yeah, you can maximize the screen.
Yeah.
Yeah, yeah, that's good.
This is fine.
Yeah,
So
right.
instead of looking at, suppose, so what I am trying to say is that you are not able to enumerate the entire population, you are taking samples of two. So if you're taking a samples of two, what are the different ways you can draw samples of two? That's what this table shows, that the ages are 18, 20, 22, and 24. So you can draw samples. How many samples can you draw if you draw it with replacement? So you can draw two samples with age 18 and again 18. Okay, then 18 and 20, then 18 and 22, then 18 and 24. So 18 can be combined with itself or with all other numbers, and that way you can draw samples of two. Similarly, the other ages can also be combined with other ages, and that way totally there are 16 ways of drawing samples with replacement. Okay, and if these are the two samples that you draw, and then if you take the mean of these samples, the mean of these samples are, you see here, these are the means. 18, if you take 18 and 18, then the mean is 18. If you take 18 and 20, the mean is 19. So if you take 18 and 22, the mean is 20, so on and so forth. So for every a sample of size 2, you will have an average. So you will have total 16 means. Okay. Now, if you see this table here, 18 is occurring, the mean 18 is occurring only once among 16. 19 occurs twice. 20 occurs 3 times, 21 occurs 4 times, 22 occurs 3 times, 23 occurs 2 times, and 24 occurs once. So, what is the probability? How do we take the probability of the mean? That comes in the next slide. If you see the probability, the number of times or the proportion of occurrences of these numbers, if you see this, then the probability of having 18 as the mean is 1 out of 16. Probability of having 19 as the average is 2 out of 16. 20 is 3 out of 16. 21 is 4 out of 16, and so on and so forth. So what is happening is that although when you had only uh, actual numbers of the ages as 18, 9, 18, 20, 22, and 24, when you draw samples, repeated samples from the same population, and you plot a graph or a histogram of this, you see it follows a symmetric distribution. Understood? So that's what the whole concept of central limit theorem is, which says that, so what's happening is, if you take the samples, if you take the mean of these observations, the mean of these observations, I mean the mean of the averages, there are 16 averages, and if you take the mean of all the 16 averages, the mean again comes out to be 21. So we saw the population mean is also 21, and the sample average of the averages is also 21, and the standard deviation for this mean is 1.58. So if you see this graph, then the next slide that I show is that for the population, it is a uniform distribution. Every number occurred only once, 1 out of 4 times. But when we plotted the means, when we plotted the means, we found that the mean follows a normal distribution. So that's what I said, that the central limit theorem says that the whatever be the distribution in the population, when we draw large samples from that population, it tries to follow a normal distribution. That's what the whole concept of normal distribution is. So then coming back to my slideshow. So the properties of the summary measures is that the sample mean therefore gives us an estimate of the population mean. So if we are not able to enumerate the entire population, doesn't matter. We will take a small sample from the population, and we draw inferences from the sample. And the mean of the sample gives you an estimate of the population mean. However, the sample variance and the population variance are related by this formula: 1 minus 1 by n times the sample variance. Population variance is equal to 1 by 1 minus n times the sample variance. So therefore, based on the small sample, it is possible for us to draw inferences for a larger population using statistics. In statistical inference, we draw inferences from a sample to the population, and if the data is a continuous data, then usually we use the normal distribution or the student's t distribution, and these distributions can be used to test a single sample or a single mean, or it could be to compare several means from different data sets. It could be used for testing the proportions also. And if we are looking at at categorical data, then the sampling distribution that is used is the chi-square distribution. And if we are looking at several means, then there is a distribution called the F distribution, which is used for decision making. Now, I'll skip this. Then we talk about estimation and what are the estimation procedures. We have two types of estimations: point estimation and interval estimation. The point estimation uses the information in the sample to arrive at a single estimate, and that estimated is considered to be closest to the true value. But is it really close to the true value? No, it is not close to the true value. For example, that we saw just now, the sample mean is the best estimator of the population mean. It may not be equal to the population mean, but it is considered to be the best estimator for the population mean. And the standard deviation is considered to be the best estimator for the population standard deviation. Now, whenever we estimate some value from a sample, and as I said, it could be that the sample may be too small, and it may not be able to give you estimates very close to the true population values. So in such cases, we use a term called confidence intervals that indicates that gives you a reliability of the of the estimate that you have derived from the sample, and it tells you what is the probability of having the population value within that interval, and that is called the confidence interval. And it gives you a range of values and with a probability attached to it. And if the probability if the specified probability is called the confidence level, and the end points of the confidence interval are called the confidence limits. So you must have seen in papers, they give a number and then they give 95% confidence interval with a lower limit and an upper limit. So it is assumed that if such samples are drawn repeatedly 100 times, then 95% times there is a possibility that the true population value lies within that interval. And that is what the confidence interval means here. It gives you a margin of error on either side of the point estimate that you uh, derive from a sample, and it gives you the probability of occurrence of the true population value within that interval. The common confidence intervals are the 90%, the 95%, and the 99% confidence intervals. And all these for a medical student may be uh, difficult to understand, but you try to just understand the fact that whenever we do clinical statistical decision making, then this confidence interval concept is very important. And generally, for all statistical purposes, we take a confidence interval of 95% in all our calculations. And this is a normal distribution, bell-shaped distribution, and we assume that 99% of the values, it is a standard normal curve. It is also called a standard normal curve, and we assume that if you have data coming from a large population, then 99% times there is the possibility is that it lies within a standard value of -3 and +3. These are standard normal values. So I think this will all come later. Today is the first day, and I'm talking Greek and Latin to you, but probably you will learn all this during the course of this 1 week training program. And then 95% data lies between -2 and +2, and it is actually -1.96 and +1.96, and 68% of the data lies between -1 and +1. So this is the standard normal curve. They're talking about, I think I will not talk about this and quickly come to hypothesis testing. So then comes the hypothesis testing, which is an important concept to understand, because that is the place when actual decision making is carried out. So how do we, in statistics, how do we prove or disprove an assumption? So we always start in hypothesis testing. We always start with an assumption about a population parameter, because as the population parameter or population value is not known. It is an unknown value, and we are trying to arrive at as close as possible to the population value using sampling techniques and statistics. So let us assume, for example, that the mean SBP of men in Delhi is 135 HGMM. Okay, so this is an assumption that we make, and we try to prove or disprove this assumption using hypothesis testing. So we say that a statistical hypothesis test is a method of taking statistical decisions using experimental data, and it is used to investigate the validity of a claim about a hypothesis about a population value. And how do we investigate that claim? We start with a null hypothesis, where we say that a null hypothesis is a hypothesis which is harmless. You know, it doesn't decide on either side of a decision, but it will just say that uh, this is not true. For example, if we are assuming that the SBP of men of Delhi is 135 mmHg, then H naught or null hypothesis says that it is not 135 mmHg. It is not equal to 135 mmHg. Okay, and then the alternative hypothesis says, or it could be the other way around. It is equal to 135 mmHg, and the alternate hypothesis is always opposite to the null hypothesis. And whenever we are trying to prove something, we state it as an alternate hypothesis. For example, in our example, if we are saying that we assume that the blood pressure of men in Delhi is 135, then that is equal to 135 becomes a alternative hypothesis for it. And the null hypothesis will be the opposite of alternate. And what is that null hypothesis which is opposite to alternate? That is that it is not equal to 135. So we set up these two null hypotheses in hypothesis testing, and then we create this 2 by 2 table, where we are trying to decide or do a test against the actual situation. So the actual situation could be that the hypothesis is true, or it could be a situation that that whatever you had assumed is not true. There could be only two possibilities. Either your assumption is true or your assumption is not true. So that could be the actual situation. But when you do a statistical test using samples drawn from that population on for which you are testing the hypothesis, and you with whatever sample you draw, you come to the decision that your assumption is not true. If your assumption is not true when actually it is true, okay, assumption is not true when actually it is true, then you are making an error, and that error is called the type 1 error. And similarly, when you say that you are saying that you are accepting the assumption when actually the assumption is not true in an actual situation, then again you are making another error, and that is called the type 2 error or the beta error. So we make two types of errors when we draw samples from a population. Either you do not agree with the assumption or you agree with the assumption. Whichever, either ways, you are making some error. So you will have to, the whole point of doing a null hypothesis is to uh, live with this error. You cannot change that error because you already the universe is constant, but you are drawing a sample from the universe and you are trying to minimize that error. So how do we minimize that error? You minimize the error by using statistical techniques. Now this is the basic way you set up a hypothesis, and then you draw conclusions based on the samples that you draw. So there are 6 steps involved in hypothesis testing. You have to state the null hypothesis and the alternate hypothesis. You have to test. You have to choose the level of significance. The level of significance is the type 1 error. You have to fix the type 1 error, and also fix the type 2 error. And because type 2 error then gives you the power, all that will come later on in your training program. So type 2 error gives you the power, and then you have to fix these two, and then you have to select an appropriate test statistic and an appropriate sampling distribution, and then you have to use the published critical values and the rejection regions and non-rejection regions, and collect the data and compute the value of test statistics based on this. Okay, so now then I quickly skip this and then come to the main topic of this lecture, and that is the various study types. This will be more interesting to you because it is less of theory of statistics and more of practical study designs. So when we do research studies, then there are various study designs that can be adopted to conduct research. And
Sorry to interrupt you, ma'am.
hmm,
Ma'am, can we take the 5 minutes break if you permit?
yes, yes,
We'll give you the 5 minutes break.
yeah,
Then you will be started.
okay.
Okay.
Hypothesis generating studies, followed by, and the last level of evidence is given by the expert committees or expert reports. Based on the level of evidence and recommendation, the strength of evidence is created. The grades of evidence range from A grade that supports the intervention to the E grade that is against the intervention. Most of our well-defined, well-designed RCTs provide A grade evidence, which is the best evidence. So descriptive studies. Now, descriptive studies are the first scientific step into an area of inquiry because they are hypothesis generating studies. They are usually hypothesis generating studies that are employed for planning resource allocation and obtaining formal diagnostic information on prevalence, natural history, and patterns of disease. One of the major limitations is that these studies cannot make causal relationships and are often inferences that are drawn from by overstepping the data. You draw inferences based on not the data that you have collected, but you go beyond that and try to extrapolate from the collected data. So hypothesis generating studies are still useful because they are used for planning and resource allocation. Most of the programmatic studies are descriptive studies. Then comes, there are some descriptive studies like case reports. A case report is a detailed clinical report of findings of a patient on association of an exposure and a disease. Association of the exposure and the disease of several patients constitutes a case series. Surveillance is an ongoing system of data collection, analysis, and interpretation. Correlational studies explore the statistical connection between disease in different population groups and the estimated exposures in groups rather than individuals. So correlation studies are not based on individuals, but they are based on groups. And a cluster study is a descriptive study that involves a review of an unusual number of health events. For example, it could be reports of cancer that is grouped together in time and in location. So cluster investigations are again descriptive studies that are useful, but it talks about group investigations. Then comes the analytical studies. The analytical studies are done to establish a link or a causal link between various factors that could preempt a disease or an outcome. You do an analytical study, you have any of these words in your research question. It could be greater than, it could be less than, it could be causes, it could be leads to, it could be comparing with, could be more likely than, it could be less likely than, it could be associated, it could be related to, it could be similar to, it could be correlated with. If you have any of these terms in your research question, then you are not doing a descriptive study, but you are doing an analytical study. Now, in analytical studies, the first one and the simplest one is the cross-sectional study. We've seen that cross-sectional studies are those studies in which the exposure and the outcome are both measured at the same point of time, and there is no temporal sequence between the exposure and the outcome. Then comes, what are the measures when you're doing a cross-sectional study? What is the measure of association? And for a cross-sectional study, the measure of association, again, I think the measure of association is risk ratio or relative risk, and the risk ratio is actually defined as the ratio of risk in the exposure group over the ratio of risk of the disease in the unexposed group. So the ratio of risk in the exposure group is, if this is the kind of 2 by 2 table that you draw, this on the left hand side you have exposure, yes, no, and the disease, yes, no. Then the exposed, what is the what is the count of exposed who have the disease, that is A, and total exposure is A plus B. So A over A plus B gives you the proportion of diseased in the exposure category, and the proportion of diseased in the unexposed category is C by C plus D. So the ratio of these two gives you the risk ratio, and that is a measure of association you employ in a cross-sectional study. Got it? So now, what are the advantages and disadvantages of a cross-sectional study? The cross-sectional studies have the advantage that it is fast, it is inexpensive, and it gives a snapshot of the distribution of the disease and the risk factors. It gives us the prevalence and the association, but it cannot study causality and it cannot be used for studying rare diseases. So cross-sectional studies cannot be used to study causality, nor can it be used to study rare diseases. So then comes the next type of analytical study, and that is the cohort study. So what is a cohort? A cohort consists of a group of persons who are investigated forward in time, starting from an exposure till they get the outcome, or they are till till they till the outcome that we are interested in. Now again, cohort studies could be retrospective cohort studies where you start with the outcome and go back in time and see that whether uh, there was there were specific exposures that could have resulted in this outcome, and that's the retrospective cohort study. Or it could be usually it is a prospective cohort study. You start with an exposure and follow up over a period of time and end up with the outcome. And that they are also, these are also called concurrent cohort studies. Or it could be ambidirectional also. You have one group of people who start with the outcome and go back to the exposure. Parallelly, you have another group of people who are studied from the exposure till the outcome. So these are the type of studies that are used to see the etiology of a disease and the natural history of the disease. In a cohort study, we need to clearly define the population at risk, which are both the exposed and the unexposed groups. The exposure and the outcome should be clearly defined. The controls should be similar to the exposed in all aspects except the exposure. The loss to follow-up has to be accounted for, and the confounders have to be accounted for. Again, in a cohort study, the measure of association is the relative risk, just like in a cross-sectional study. The relative risk is the measure of exposure, where you're looking at measure of association, where you're looking at the risk of ratio of risk of disease in the exposed and the unexposed, and the formula remains the same. Now, what are the advantages and disadvantages of cohort studies? The advantages of cohort studies are They allow complete information on the exposed group. They provide temporal sequence of exposure and the disease. There is an opportunity to study multiple outcomes. You can start with one exposure and you can study multiple outcomes in that in that period. It helps us in estimating the incidence rates and the relative risks, and it enables to study rare exposures because you start with an exposure and you end up with the outcome, and it is easily understood by the epidemiologists and the clinicians. So these are some of the advantages of a cohort study. However, cohort studies have disadvantages also. The disadvantages of cohort studies is that it is not suited for rare diseases. Why it is not suited for rare diseases? Because it may take a long time from exposure to outcome, and it is not cost effective to invest in cohort studies because it takes a lot of time and energy and a lot of resource. Long time duration between exposure and disease is not suitable for cohort studies. Exposure patterns may change over a period of time and may make the results irrelevant. There is a high chance of loss to follow up if it's a long duration study. It is expensive, and because the sparse baseline data is not available. The baseline data could be absolutely sparse since the subjects may not allow long interviews. So it is possible that you may not get good baseline data since the subjects will not be able to. Let me just put my battery on. Okay. So there are some very interesting examples of cohort studies like the Framingham Heart Study, the Nurses Health Study, and the British Physicians Study. These are very significant cohort studies, and I think those who have studied epidemiology may have an idea about all this. Then comes the analytical studies called the case control studies. In case control studies, the study groups are those with the outcomes and the controls are those without the outcomes. We start from below. These are the cases with the outcomes and these are the cases without the outcomes. And then information about their exposure is investigated by going back in time and by collecting data from their past history. And when they go back in time, the one gets an idea about the kind of exposure that they have, and then retrospectively we try to analyze whether that exposure could possibly have impacted the outcome. And that's what we do in a case control study. So what are the major steps here? Case control studies, we should have the selection of the case group is very important. We should have clear definitions of the outcome and the clear definitions of the case. Case definition has to be clearly stated in the beginning itself. The inclusion exclusion criteria has to be clearly defined, the age range, the location, and all that has to be defined. And also in a case control study, one should look at incident cases and not at prevalent cases, because prevalent cases, those diseases which have occurred over the past many years could possibly give you different results as compared to new cases. So we always look for new cases, and it helps us in studying rare diseases also, because here moving forward in time and investing a lot of time and energy in in studying the disease from the time the person is exposed till he gets the outcome. So here you have the outcome here with you, and you're going back in time to see whether any particular exposure has resulted that outcome. And the selection is of controls is very important, because the controls should be as similar to the case as possible, except that the control does not have the disease. It should be exposed to the similar exposure, and it should have similar setup, or it should have lived in a similar condition as a case. Then only a case control study will give us the kind of results that we are looking for. So the case control studies can be community-based studies, it could be hospital-based studies, or it could be nested case control studies within a cohort. It could be prospective studies also, and it could be retrospective. But usually, case control studies are retrospective, unless you have a more complicated design. And in a case control study, the measure of association, instead of risk ratio, the measure of association in a case control study is called the odds ratio. It is the odd ratio of odds of exposure in the cases and odds of exposure in the controls. And the definition is given this way, it is AD by BC. What are the advantages of case control studies? The case control studies helps you in studying rare diseases, and even if there is a long latency in the exposure and the outcome, you can still study the disease because you're starting with the outcomes, and it can be started for short period of time, and you are less expensive, and you can also look for multiple exposures for the same disease, because you are going back in time, so you can study several exposures for the same outcome. But the problem with case control studies is that because it is retrospective in nature, there is a high chance of recall bias, and you may not get because again because everything depends on the way the patient whom you are interviewing, it how the patient reports the level of exposure, and it could be possible that the information on exposure may be incomplete. You cannot do case control studies on multiple outcomes. In the same case control study, only one outcome or one disease can be studied, and it does not give you incidence rates, because you are not progressing over time and looking for new cases, but the same the it you are going back in time to look for the disease or risk factors, or the disease the factors that could possibly result in the disease. And therefore, it is not possible to get incidence rates from case control studies. And then always for a case control study, it is difficult to get an appropriate control group which lives in a similar condition as a case, except that it does not have the disease. So it becomes very difficult to get control groups, and therefore the methodology also is a little difficult to understand for people who do not have a fair idea about the research methodology. Then comes the most important group of analytical studies, and they are the clinical trials. So what happens in a clinical trial? In a clinical trial, We have patients who have the disease, and you are trying to test a new treatment or a new drug or a new therapy or a new intervention on these patients. You have one group who have one intervention. It could be a new intervention, or it could be an altered intervention, or it could be a placebo and an intervention, or the other group, which is a comparator group, which does not get that intervention. You study the patients over a period of time till they reach the outcome, and then the outcome you try to measure the proportion of patients who have improved and those who have not improved. The fundamental principle that lies in a randomized controlled trial is that the two groups, the experimental group and the control group, must be alike in most of the aspects, and only the difference should be that one group has got one intervention and the other group has not got that intervention. So the treatment group and the control group have to be alike on an average. Then comes the most important thing, and that is randomization. Every patient or every participant in a randomized controlled trial has the same chance of receiving the intervention. That is the basis of randomization, and an allocation is carried out, and that allocation is carried out using a chance mechanism, and there the probability concept comes into the picture, and so that neither the patient nor the investigator knows in advance what treatment is being assigned. And that is how the allocation, concealment, and randomization concepts come in randomized controlled trials. And then comes the blinding, where you have to avoid consciously or subconsciously the influence of knowledge of the intervention, and to get fair evaluation of the outcomes, the investigator is also blinded, and the clinician is also blinded, and sometimes the patients are also blinded along with evaluators sometimes. So there are different types of experimental studies like open trials, single blind trials, double blind trials, and many more. So there are different, these are all studies which give you the first level of evidence if done properly using uh, the right statistical techniques. What are the advantages of clinical trial? Lot of advantages. Number one, that it gives you grade 1 evidence. It gives you grade 1 evidence, and it produces it gives you comparable groups, and randomization helps in producing randomization helps us in non-violation of statistical assumptions, because as I said before, that many of the statistical tests that are carried out in clinical studies are with the basic assumption that the data comes from a normal distribution. So by randomizing, that violation of assumption can be minimized. And the disadvantages are that the clinical trials are always done in a conditioned environment. So possibly that participants studied may not be representative of the general population. So there is a possibility that you cannot replicate the result that you get from a clinical trial over a general population. It is difficult to recruit the participants in a clinical trial, and the randomization process is difficult to comply with the physicians, and there are a lot of complexities in administering the intervention. Then comes, I will not go into the details of the different types of biases in study designs. I can only say that biases are systematic errors that distort the effects of the true effects. There are different types of biases: the selection bias, then the information bias, subject bias. There are n number of biases, and the selection bias could be due to the choice of the comparison group. It could be the choice of the sampling frame. It could be selection of the subject or the population. Information bias again comes from the measurement errors, the instrument measurement or errors in the exposure and the outcome. So there are n number of biases. You can do you can do a full lecture on various types of biases. So these biases can be avoided in clinical trials by randomization. A well-designed study provides very good evidence, and this can be achieved only if it has a reduced bias. In observational studies, bias could be assumed and acknowledged, while in randomized controlled trials, it is assumed to be free from the bias. We should do randomization, blinding, and allocation concealment to avoid bias in randomized controlled trials. But in observational studies, such biases cannot be avoided, but they can be reduced. Now, how do we avoid bias? There are different types of randomization techniques in randomized controlled trials, and these are some of them. It's a simple randomization technique where you have the simple randomization way. The
Ma'am,
other
we are getting late. It's okay. Please
Yeah, I know.
conclude it,
So
ma'am.
I think
Please.
we are
Yeah.
almost done. I am almost done. Two more slides.
Yes, yes, ma'am.
Two
Please.
more slides. Then the different randomization techniques could be the block randomization, the randomization rules, the earn randomization, and the allocation techniques are also many. Some of them are the sequentially numbered sealed envelopes, sequentially numbered containers, pharmacy controlled randomization techniques, and then there is a central randomization technique. So blinding, how does blinding help you help the randomized trials? If the individuals are blinded, if the participants are blinded, it is less likely to have biased psychological and physical responses to intervention. It is more likely to comply with trial regimens, less likely to seek adjunct interventions, and less likely to lose to follow up. And if the trial investigators are blinded, there is less likely to and less inclination to the attitudes of the participants. There is less inclination of adjusting the dose for the participants, or there is less likely of withdrawing of the participants. And sometimes, if the investigators know the intervention, there is a possibility of them likely to encourage or discourage the participants, and blinding helps us in avoiding or reducing that bias. So, the people who generate the allocation scheme should not be involved in ascertaining the eligibility, administering the treatment, or assessing the outcome. So I think this is the last slide, which I have quoted from the Nature of Statistics, and that says that he who accepts statistics indiscriminately will often be duped unnecessarily. If you should accept statistics, but you should accept it with a sense of knowledge. But he who distrusts statistics indiscriminately will often be ignorant unnecessarily. So this is a quote that I have taken from the Nature of Statistics, an old from New York Times. And that ends my talk today. That's it.
Thank you so much for your valuable.
It's a long overhaul of many things.
Yeah, yeah,
But I
actually,
think it sets your ball rolling, I think.
yeah, actually, I mean, within a very limited time, you have explained all the things in a very nice manner.
I may not have cleared, but I have set the ball rolling for you for the next few days.
Yes, yes, miss, because we will take all the lectures independently from your lecture,
Yes.
ma'am, because
Yeah.
you have told all these things. So now, participants, this session is now open for question answer or any query. Then you can take our 5 minutes for the question answer. You can unmute yourself and ask the question one by one.
Ma'am, good evening, ma'am.
Yes. Good
Good
evening.
evening. Good evening.
Ma'am,
Should
thank
I
you for
stop sharing now?
ma'am,
Ma'am,
one
please
doubt,
stop.
madam.
Ma'am, stop sharing, please.
I
Screen.
will stop sharing.
Yeah, yeah.
One doubt, madam.
Yeah,
Ma'am,
yeah.
thank you for wonderful presentation, madam. I just want to know the basic difference between incidence and prevalence, madam. That word I am not able to understand.
Incidents are new cases.
Okay,
If say for example, you are interested in knowing the number of new cases of cancer. So if you have the existing number of cases, then they are called prevalence cases. But if
okay.
you are following them over a period of time, they may not be a case today, but tomorrow, if it becomes a case, it is a new case. So those are called incident cases in epidemiology.
Time based.
Not
Okay.
time based, not time based, but prevalent is something that is already there, and incidence is something new.
Rate, no, madam. Number.
Yes, incidence rate. Rate is a
Okay.
denominator is the population, or it could be the
Okay.
person years, whatever. There are different ways of defining it.
Hello.
Okay. Thank you.
Uh, Ma'am, I have a question. This is
Yeah.
regarding the sample of population of 4 people that you explained with an example and 16 combinations. You said about replacement in that. Could you
Yes.
kindly explain it briefly, ma'am? What was that
See,
replacement about?
yeah. Yeah, there are two ways in statistics. We have two ways of sampling. One is sample with replacement, and one is sample without replacement. Say, for example, you have a box in which you have 100 oranges, okay, and you want to draw a sample of 10 oranges from that box. Then one way of drawing the 10 oranges would be you draw the first orange, and then you draw the second orange, then you draw the third orange, and you are not replacing the ones that you have drawn. Okay, so that is called sampling without replacement, where every time you draw a new orange, the probability of drawing a new orange changes. Had you replaced the first orange, then the probability of drawing will always remain 1 by 100. Okay, got it?
Ma'am, we will take the whole session on sampling theory tomorrow.
Okay,
So we
so
will discuss all these
Dr.
things.
Yadav will explain it further.
Yeah, yeah.
So that is what it means by replacement and without
Yeah,
replacement.
yeah. We will take all these queries in sampling session. So if any query from this session only,
Sir,
then you please discuss.
sir, I have one doubt, sir.
Yes, please.
Hello.
Yes, yes,
Yeah,
please.
What is the difference between odds ratio and relative risk ratio? Relative risk, odds ratio and sorry, attributable risk and
relative risk.
relative risk. Yeah.
Odds ratio and relative risk are two different things. Odds and probability are different. Risk ratio is actually the risk of probabilities. Probability of occurrence of the disease in the exposed group over the probability of occurrence of the disease in the unexposed group. So this is
That is
risk ratio is actual risk of ratio of probabilities. Okay,
okay.
but the odds ratio is not probability at all. It is the odds of occurrence. There is an odd of occurrence. So there is a difference in the way you express odds ratios and interpret odds ratios and risk ratios.
Attributable risk, ma'am.
No, attributable risk is something different. Attributable risk actually gives it tells you how much risk is attributed due to a particular exposure. Okay, that quantifies the risk for that exposure. Attributable risk is different, altogether different.
Okay. Box sampling, ma'am, can you explain box sampling, ma'am? When
What
we
sampling?
box sampling. Box.
Box.
Yeah.
No, I didn't get you. Box sampling?
I think today's class, I think we should discuss what has happened. Nothing beyond that.
Hello. Yes, we can discuss only those topics which are discussed today's session. So you all are.
Yeah, that is better.
Question.
Otherwise, we close it.
Ma'am,
Yes.
Good evening, ma'am.
ma'am, about the biases.
Yeah.
And
One by one, please. We will take one question at a time.
Hello. Hello.
Others can leave.
Yes.
Hello.
See, this is a broad overview of various topics that will be taken up during the course of this workshop.
Yes.
I think I have just given you a broad overview.
Yes. Many of your topics will be discussed in the near future in upcoming.
Exactly.
Are you sharing the PPTs?
Yes. We will share the PPTs and video recordings of all the sessions.
When? Today or
Yes. In the day. Today only. After this session.
After this. Okay.
Ma'am, what
I
you
have a
have
doubt.
Yeah.
One by one, please.
Can I ask, ma'am?
Yes.
Yeah.
Ma'am, I have a doubt regarding CTRA registration, ma'am. Ma'am,
Yes.
is it possible to get a retrospective CTRA registration nowadays?
No, Madhumati. Earlier there used to be this retrospective registration, but now we have made it compulsory that before the first patient is enrolled, the study has to be registered in CTRI. It has to be prospective registration only.
Okay.
Ma'am, I want to
Thank
ask
you.
a question regarding CTRI itself. I wanted to ask, do we have to register even a cohort and case control studies in CTRI?
Ideally no, but you know what, people don't I don't know why people register even observational studies in CTRI, although CTRI has a provision of registering observational studies, but ideally there is no need to register an observational study in CTRI. You can do an observational study without registration.
So if there are any other question, we will take by mail or WhatsApp group.
Sir, I have just one question. Can I ask that?
Yeah, it will be the last question.
There is in your second last slide on randomization. Can you please elaborate how we do that central randomization? What is earned randomization?
Oh, I will have to give you more details. You can write to me by email. I'll give you.
Yeah, you can write the email, and we will send the PPT.
Dr. DK sir, please summarize.
Email to.
Yeah. Thank you.
Hello, ma'am, just a minute, ma'am. Ma'am, within short span of time, you explained more and more things, ma'am. It is a very wonderful session. It is. I have given a lot of knowledge. We acquired many things from you.
I have only
Thank
touched
you
the
very much.
topics. I have just touched the topics. Every
what
topic
short
requires
span of time.
detailed.
Yes. I know it is not possible
Short
to cover
span
all
of
the
time. It is
systems.
very difficult.
All the topics within.
Ma'am, I came from biostatistician. As a biostatistician, you know, ma'am, within short span of time, you explained more and more things, ma'am. We got it more. We acquired more knowledge from you, ma'am. Thank you very much.
Thank you, Doctor. Thank you, Dr. Ganesh.
Thank you.
Where do I email?
Okay.
Where to email?
Ma'am, can you share your email with chat, or I will.
Yeah, I can send it. You have my email ID, isn't it?
Okay. Or you can write in the chat box, ma'am, if possible.
I can. This is my email ID.
Okay.
menongr.hq@icmr.gov.in.
Repeat, madam.
menongr.hq headquarters @icmr.gov.in.
Ma'am, will you write it in chat box?
Yeah, I've already written.
It
Can
is
you
not.
see it?
Don't worry,
Ma'am, we will share in the WhatsApp group. So don't
When we
worry.
will send the PPT and video, the email ID of the ma'am will be sent
Yeah, yeah.
also. Okay,
Yeah, there is in the chat box.
Don't
In
worry.
the
When
chat
I will
box.
send the PPT and video, you will get the email ID also.
Okay. So thank you so much, participants, for your wonderful patience, and thank you so much, ma'am, for this your wonderful session. And we will
Thank you so much.
see you soon. Thank you so much, ma'am.
Thank
Please,
you.
ma'am, please send your PPT
Myself, Dr.
so that we
SK.
can give them.
Okay. I will.
Thank you, ma'am. Thank you.
Thank you.
Thank you.
Okay. Thank you.
Thank you.